Well, thank you for the invitation. It's a pleasure to be there virtually. So I will talk about a curious situation with supersymmetric black holes, where in some sense we have time without having a Hamiltonian. This is based on a couple of papers, a short paper and a long paper describing the same idea that we wrote with these three authors. But I was asked to give an extended introduction, so we'll first review some general ideas, and then we'll get to what we actually did. So let's start with black holes. So one important idea in the study of black holes is that we think that black holes, as seen from the outside, can be viewed as quantum systems. And this sometimes we call the central dogma or central hypothesis. So the idea is that if you look at the black hole and you do any experiment you can imagine outside the black hole, you can send particles into the black hole, look at the Hawking radiation that comes out. The idea is that those experiments can be reproduced by some Hamiltonian that acts on a system of qubits, where the number of qubits is of order the area of the black hole horizon. So this implies, in particular, information is not lost into the black holes and so on. Now, the hypothesis itself does not tell us what the Hamiltonian is. In some very special cases, we think we know what the Hamiltonian is, but that's even those cases, it's a hypothesis that those Hamiltonians describe the black hole. Now, let me just remind you one aspect of the geometry of the simplest black hole solution. So the simplest black hole solution is the black hole solution without matter. That's the one that Schwarzschild found. And that solution has some region that looks like the exterior of a black hole, that is joined with a second region that looks like a second exterior of a black hole, and they're joined through the interior. So let me briefly review this type of diagrams. So here on each point on the diagram, there is a two-dimensional sphere that only shrinks to zero at the singularity. And then the vertical direction is roughly time, and the horizontal direction is roughly space. And those, space, I mean the radial direction. And those two dimensions of time and the radial direction have been, the metric has been shrunk by a rescaling factor that preserves angles, and in particular has brought infinity to a final location, and has preserved the direction of light rays, which move here at 45 degrees. So the central feature of a black hole is that there is a horizon, so a light-like ray or set of rays, which separates two different regions of the space-time. So the point here can send the signal to infinity to someone who's far away, and a person here cannot send the signal there. So this interior region is not observable from the exterior. Now, if you have a black hole that collapses from matter, you don't get this whole geometry. You only get a portion of the geometry outside the matter. And then when you have matter, you have a different solution that typically does not have the second side, has only one exterior. It also has an interior. But this is a curious solution which has two exteriors. And the question is how to interpret it in the light of that hypothesis we discussed before. And the idea is that we can apply this hypothesis independently to each black hole, and we can replace each black hole by a quantum system. And the idea is that these quantum systems are entangled with each other. And these quantum systems are very far away, so there is no direct interaction between them. So the idea is that this entanglement, as long as it is in this particular state, which is the thermophile double state, so it's a state where we take all the energy levels and we sum over all the energy levels with weights which are similar to the thermal weights. In fact, if we trace out the left side, we get precisely the thermal density matrix. And for that reason, that state had been studied before. So the idea then is that entanglement can give rise to this geometric connection, or the geometric connection is called the Einstein-Rosen bridge, and entanglement is it's EPR correlations in the famous Einstein-Podolsky-Rosen paper. Now, in this relationship, we can think about the Hamiltonian acting on the left system and the Hamiltonian acting on the right system, and that the difference between the two Hamiltonians would annihilate this thermophile double state because the two energies are equal, and that becomes an isometry of the of this solution, and is the isometry that well corresponds to time translations far away, but near this point. So, but most precisely at this point, it acts as a boost. So, and that's a general feature of black holes, which and then the presence of horizons in general, which is that the time-like isometry far away can become a boost. Well, does become a boost in the near horizon region. Now, perhaps the most interesting question in this field is to understand better the nature of the singularity and the emergence of this time direction. Notice that the time direction we had far away in the region in the interior becomes a space-like translation. So the question is, how does this time direction emerge, and what is the singularity? Now, I will not be answering this question. I just mention it just to give you a general framework and sort of high-level motivation for the study of quantum black holes. Of course, we hope that by understanding this question, we'll understand the beginning of the Big Bang, but that's just the whole motivation to this field of the study of black holes and quantum gravity. So now, as we will try to analyze somewhat simpler problems, as often we do in physics. So we'll study problems with more symmetries. So we'll study certain black holes which have more symmetry. So I will now review this type of black holes. So we'll focus on so-called near extremal black holes, and we will explain why they have more symmetry. So this involves charged black holes, so black holes that carry some charge. It could be electric or magnetic charges. And such black holes have a constraint on their masses. So their masses has to be bigger or equal than their charges in some units. And when the mass becomes very similar to the charge, then the black hole develops a long throat. So the horizon becomes more and more distant from some point here in the exterior. So let's say you sit at some point here and you take this extremal limit, then the horizon sort of goes deeper and deeper inside this throat. This throat has the property that it has a sphere of almost constant radius. So this and then the time and radial direction combine to form a space with a two-dimensional space, so 2 dimensions, time and the radial direction, and those 2 dimensions form a space with constant negative curvature, which is the Lorentzian analog of hyperbolic space, of 2-dimensional hyperbolic space, and it's called 2-dimensional anti-de Sitter space, or ADS2. Now here, the n means that it's nearly ADS2. It's not exactly, because the radius of the 2 sphere is not constant, but changing very slowly as we go out. So we see that in this limit, the black hole develops more symmetries, because beyond the time translation that we have for any static black hole solution, we also have additional isometries, which are the isometries of this 2-dimensional space with constant negative curvature. So it's like similar to the fact that that hyperbolic space has 3 isometries, and that number 3 is the same number as the number of isometries of a 2-dimensional sphere. In fact, ADS2 and a sphere are kind of related by analytic continuation, so that they have the same number of isometries, though the group is slightly different. One important point is that the gravitational redshift becomes very, very strong as you go down. So that means that an excitation that is somewhere here, let's say at a fixed distance from the horizon, will look like it has very low energy from the point of view of the outside observer. And that energy would become lower and lower as we take the limit closer and closer to extremality, because this throat becomes deeper. You can think of this throat as a big gravitational potential well. So something which is down here has a lot of trouble sending signals to the outside, and would have a lot of trouble escaping from the black hole. So the idea is that to focus on these black holes at low energies, so that we are somewhere close to the horizon and far from the top of the potential. And in that limit, the system is described by purely this ADS2 region. And the idea is that quantum mechanical dual, so that remember that central hypothesis we discussed in the very beginning, said that the black hole as seen from the outside can be described by a quantum mechanical theory. And the idea is that because this theory has extra symmetries, that quantum mechanical dual will also have extra symmetries. And the extra symmetry of the quantum mechanical dual is a rescaling symmetry. So it's a time rescaling symmetry. Sort of, it's a bit like a critical point. So it's a kind of critical point, but in quantum mechanics as opposed to in quantum field theory. So it's a scaling symmetry, and then one more symmetry, which is the conformal symmetry. So the symmetry group is called SL2R. So it's some analytic continuation of SU2. It has three generators, as we said. One of them is the time translations. Then there is time rescalings. And that time rescalings corresponds to the motion along the radial direction in the ADS2 region. And then we have one more isometry. And so the idea is that when we look at physics in this ADS2 region, we are talking about a nearly critical quantum mechanics system. Now, the word nearly, it's important here because because the black hole here has finite entropy, and we cannot have a quantum mechanics system with exactly scaling symmetry. That would imply we either have a continuous spectrum or a spectrum which is completely localized at zero energy. So this symmetry is only approximate, but it can hold very, very close. It could be very close to a symmetry for systems with very large number of degrees of freedom. Now, an example of a quantum mechanical model of this kind is this Sashlev-Yekitayev model, which maybe you've heard about, which has this nearly critical low energy regime. But in case you didn't hear about, I'm just going to briefly mention it. So it's a very simple model that involves interacting fermions. So n interacting fermions, n Majorana fermions with quartic interactions with random couplings drawn from a Gaussian distribution. And so if we go to low energies, but not too low, so what that means is that there is here a particular scale which can call J, which is defined so that at energies of order J or temperatures of order J, the system becomes strongly coupled. So at higher temperatures, it becomes very weakly coupled because this system in the UV is just free. But the interaction is relevant. It becomes more important at low energies. And the transition point is temperatures of order J. So we go to temperatures much smaller than J, but not parametrically smaller in N. So in this particular regime, we have a nearly scale invariant theory. So that's the simplest regime to analyze. And what that corresponds is if you were to diagonalize that Hamiltonian, the Hamiltonian would have a more or less statistically symmetric spectrum because the couplings were random with either sign. And then we are interested in the end of the spectrum here near low energies, but we are capturing a large number of energy levels. We don't focus on the very last energy level or the last, let's say, 2 or 3, but we are focused on an exponentially large number of levels that will be the low energy region we considered in the beginning. So to analyze this region, we can perform a large hand summation of diagrams. I will not give the details, but that's a relatively standard technique, and it gives a scale invariant theory at low energies. But then we can consider 1/n corrections, and it turns out that these 1/n corrections break the conformal symmetry. And there is in particular a low action mode, that becomes important at low energies. And this mode needs to be exactly quantized, and we can call it a kind of time superfluid mode. So it's a mode that you can think of it as related to time reparametrizations. And it breaks, in particular, its action breaks the conformal symmetry. Now, I will not discuss in detail how that works, but I will discuss it in terms of its impact on some observable. So let's consider an observable such as the entropy. So we're trying to calculate the entropy. Now, one feature of these extremal black holes is that in the classical approximation, they have a constant entropy because the size of the two-sphere is constant. And indeed, in these systems, like for example SYK, we have a leading term in the entropy, which is just constant, independent of the temperature. And then there is some correction, which is linear in the temperature, some classical correction. And when the temperature goes to 0, indeed, this term goes to a constant. And indeed, the constant entropy is a result which is conformal invariant. It's invariant under rescalings of temperature. And this correction breaks a bit the conformal symmetry. And so this is what you would expect if you had a conformal fixed point at low energies. So you would you might have some correction as you go to higher energies, but as you go to very low temperatures, you would have a completely constant term. And this is what you get by the leading classical limit. But when you consider the quantum corrections, you find a term that does not have the n-dependence, but a term that becomes important at low temperatures. So at low temperatures, this logarithm starts growing, becomes negative, and starts reducing the entropy beyond, so starts reducing the entropy, okay? Of course, it does that slowly, first because it's a logarithm, and second because it doesn't have the n in front, so slowly the entropy starts decreasing as you go to lower and lower energies. Okay, so that's what happens in the case of SYK, and this term comes from the quantum mechanics of that mode that we discussed and was computed in the literature. I'm only giving you the final answer. I'm not telling you how it was computed. But I would like to mention the connection to this nearly ADS2 gravity. So as I mentioned before, the gravity action. So this is just simply the negative of the gravity action is some constant plus time times some other constant. Sorry, not time, the temperature times some other constant. So for low temperatures, we have the large N answer, so something that qualitatively agrees with this. Now, one thing we can already see from this geometry is that there will be a mode that has very low action. And this we can see very simply as follows. We see that the action of the system becomes almost constant, so proportional to S0 at low temperatures. On the other hand, the physical configuration of the system or the geometry that doesn't go to a constant. In some sense, it's very different as we go to low temperature. So the length of this throat grows as the logarithm of the temperature. So it becomes bigger and bigger. So we have very different configurations with very similar action. And what that means is that we have a very low action mode. And this mode needs to be quantized, and that's the same as this time superfluid mode or Schwarzian mode that appeared in the SYK model when you look at it in detail. So I'm just giving you the intuition for why we expect to have a very low action mode just from looking at the answer. So the argument involved looking at the answer for the action and also the shape of the geometry. Now, what's the connection between ADS2 and SYK? So we have two different types of theories. So we have the SYK model and near extremal black holes. We can take a low energy limit in both cases. And here we concentrate on the ADS2 gravity, here in the low energy limit of SYK. And that low energy limit in both cases can be separated into two parts, a part that is essentially conformal invariant, and a part that has to do with this time superfluid mode or time reparametrizations. And there's a similar reduction in this case of ADS2 gravity, that there is a part that we can view it as a quantum field theory in ADS2, so fields propagating on a rigid ADS2 geometry, and a mode that has to do with the boundary dynamics. Now, this part that involves the reparametrization and the breaking of conformal symmetry are governed by exactly the same action. So this action is exactly the same, and it's essentially determined by the pattern of symmetry breaking in both cases, which is the same. However, there are other features of the model which are not the same. So this conformal invariant part does not have properties which are identical to what we expect for quantum field theory in ADS2 in a space with very large radius. So the two models share some things in common, but they have also some differences. But the things that they share in common are determine many observables at low energies, in particular the low temperature entropy. So the fact that the leading correction to the low energy limit is linear in the temperature as opposed to any other power of the temperature, that's determined by this action. And then there are various more sophisticated observables, such as the chaos exponent or something related to the traversability of the wormhole or teleportation that I will not discuss in detail. But so there are many features that are very similar. And so this relationship has been very useful for understanding aspects of, in particular, quantum aspects of black holes. Now, we will now make one more simplification. So we'll consider even more special type of black hole. So we'll consider supersymmetric black holes. Supersymmetry is a symmetry relating bosons and fermions. And for our purposes, the important point is that it simplifies some computations. And so we can consider black holes in supersymmetric theories, in particular in supersymmetric gravity theories, or otherwise called supergravity theories. And there are in those theories black holes which have the mass equal to the charge, or these extremal black holes, actually preserve some supersymmetries, and so they correspond to quantum mechanical systems which have extra supersymmetries. So we'll have more symmetries, and this in particular implies that there is a large number of exactly degenerate states giving rise to the extremal entropy of the black hole. So the black hole with M exactly equal to Q will have a non-zero entropy. Now, as a side comment, I will mention that there is also a supersymmetric version of the SYK model, and we'll discuss it in more detail later. But that correspondence we had mentioned before for general extremal black holes also holds for these more special supersymmetric cases. So we'll now review some results for the partition function, which is the same as saying that these are results for the thermodynamics that includes the quantum corrections due to these boundary gravitons or boundary modes or time superfluid modes. So we include the quantum corrections due to that mode, and then we'll see what we have in each case. So this plot here is just a simple restatement of the entropy formula we had before. So rho of E is just simply the exponential of this entropy. And at least that's what it is here for relatively, well, sorry. This is the entropy as a function of the temperature. You can take the exponential of this and then do a Fourier transform so as to express it as a function of E of the energy. And then you find that a rising function. So we have an overall function factor in the density of states, which is related to the extremal entropy. So this overall constant. And then we see that the density of states decreases at very low energy. So it's not constant, as we might have naively thought just from these two terms. And this fact that it decreases is related to this logarithm. Anyway, so one can compute this either from the black hole picture. Of course, we'll get the same for the SYK picture because this answer depends only purely on the aspects of the model, which are the same in both cases. So now we can consider the same thing, but in a theory with supersymmetry. And in that case, this time superfluid mode has also some fermionic partners. So besides the length of the wormhole, we can also act with the supersymmetric transformations, and we have some additional fermions. And this implies that it will have different quantum properties at low energy, since we have new low energy degrees of freedom. And I'm not discussing the calculation, but it turns out that once you do that calculation, the difference is that now zero energy is special. So at zero energy, we preserve some of the supersymmetries, and we have a large number of states, exponentially large, so e to the s naught, so this, which have exactly zero energy. And in addition, then we have also in this approximation a continuum of states. Yeah, perhaps I should have mentioned that when we do these computations, we are neglecting the possibility of changing the topology of space-time. And in that approximation, we see that the spectrum is continuous. So that was a feature also of this answer. Of course, in an exact quantum system, we expect the spectrum to be discrete. But that discreteness of the spectrum involves energy spacings which are exponentially small in the entropy, and we think that those would come from corrections that involve different space-time topologies. Here we're fixing the space-time topology, and we are quantizing summing over all geometries with that topology. So in this approximation, we see a continuum that starts with a gap, and the gap is small, but not exponentially small. It's if you wish, it's a relatively large gap compared to the spacing between the eigenvalues, but relatively small compared to other properties of the black hole. So when you work out what this gap is for let's say a black hole in flat space, the natural energy scale is 1 over the radius of the black hole. So that's the energy of a massless particle with a wavelength proportional to the size of the black hole. And this gap is smaller by a factor of the entropy of the black hole. So it's quite small, but it's not exponentially small. And it's also this factor is the same as is given by the inverse of a length scale, which is the same length scale that appears in the coupling for this boundary mode. So the same place where the same energy scale at which this mode becomes strongly coupled is the energy scale at which the gap develops. Now, one question we would like to understand is what happens to the gravity solution at very low energies. So we are interested in going to energies much smaller than the gap, so that only these ground states survive. So here maybe I should have mentioned that here we see some of the simplicity of the supersymmetric case, and part of the simplicity is that, well, we have a large number of states with zero energy separated by this gap. So this enables us to isolate the physics of just these states by going to very low energies. And that's what we are trying to explore. And this is a possibility we have in these supersymmetric cases, but we don't have it in the non-supersymmetric cases, because in those cases, the density of states becomes very small. And if we wanted to find the lowest energy states, there would be very few states. And it's not obvious that large N methods would work in that case. But here we have lots of states, so we expect large N methods to work in describing some of the states, in describing the physics at low energies.
So, sorry, can I ask one quick question?
Please. Yes.
So the gap is order N, or
the gap is order 1 over N.
Yes.
Yes. The entropy is of order N,
right,
and then the gap is 1 over N. Yeah, I should have perhaps put a formula with the N dependence.
But in the bosonic SYK case, we always take N to be very large, and then always consider the energy J beta is less than N. But now we take very
yes, exactly. Now we are going beyond that limit that we discussed. So we discussed this limit here. So this is the limit in which the theory is scale invariant, and we don't have to worry about the quantum corrections due to the boundary mode.
Right.
So we are now relaxing this this condition, right?
I see.
And relaxing this condition is something we can do. And all we need to do to relax this condition is to include the quantum mechanics of this boundary mode. And that will be okay as long as this is also much smaller than e to the n. So, but
thank you.
Yeah, perhaps. Yeah, but by the way, please ask me questions. Please interrupt me, ask me questions. Those interruptions are quite welcome. Okay, so by the way, so in these systems, the third law of thermodynamics is not obeyed. And that's due to this extra symmetry that the system has. So it has these supersymmetries that is protecting this degeneracies. So it looks like we have a kind of frozen system, and because we have all the states have the same energy, and so we expect essentially no dynamics. And certainly we have no boundary dynamics in this system. Now, as a first comment, side comment, is that the number of states that we has been studied and in great detail for the supersymmetric black holes, and their entropies match beautifully with some index computations or some computations of the degeneracy of the black hole degeneracies. This is something that started with the Strominger-Baffa paper in the 90s, and people have continued, and there was actually this paper today providing some further beautiful matching. Now we'll take a closer look at the gravity solution when we take the Lagrange limit and see what happens in this case. Well, first a preliminary comment. So when we take the Lagrange limit, this throat becomes larger and larger. And as I mentioned, there are quantum fluctuations of the length of the throat. We can think of that in the following way. We can think that we have some ADS2 space, and that there is some boundary of this ADS2. So we don't have the infinite ADS2 space, we have only a portion, because as we go up, at some point, we will match it to the 4-dimensional space. So we have this red line is where we are essentially matching the ADS2 to the 4-dimensional space, but that red line can have some quantum fluctuations. And that's, we can think of that as a boundary gravitational mode. So in 2 dimensions, gravity has no local degrees of freedom, but once you introduce this boundary, we have a boundary quantum mechanical mode living here. And that's related to the fluctuations of the length of the throat, for example. Now, these fluctuations affect the length of the throat, and they blur the physics for the observer looking from the outside. So they make the physics as viewed from by this observer a little more complicated. But the inside observer seems perfectly happy living in a large space-time and does not see any particularly large quantum corrections. Now, what more can we say? So we said that we can calculate the entropy very nicely, but there are other questions that we can ask about this geometry. In particular, there is more to the black hole than its entropy, and so we like to understand the details of the ADS2 near horizon geometry, and in particular, eventually we'd like to understand the physics of or the experiences of this observer. I'm not going to answer this question now, but that would be our eventual goal. So one thing that was important for our paper was the fact that there's more information in this ADS2 theory, and that is its correlation function. So we developed methods to calculate correlation functions in this geometry. And our technical results involving computing some of these correlation functions. Now, there are many previous results computing ADS correlators in ADS-D with D bigger than 2. And the basic idea in those cases is that we can compute those correlators as follows. So we have some ADS space, which has some boundary and some interior. And then we fix some points here on the boundary, and we insert some operators at these points. And then we consider Feynman diagrams in ADS connecting these lines in any possible way. There could be bulk interactions and so on. So this denotes the sum of all those Feynman diagrams. Of course, the simplest diagram might be just a free particle propagator between these various lines, various points. And these are sometimes called Witten diagrams. But so this is the general situation in ADS-D. So the correlators can be well computed by, at least in the large N approximation, by considering quantum fields in a fixed ADS geometry. But in 2 dimensions, the situation is a bit more complicated. One might have thought that 2 dimensions would be simpler, but in some sense it's a bit more complicated. And it has really only been understood within the last few years. So the new feature is this boundary gravity mode that we mentioned a few times. that becomes strongly coupled, and therefore we need to quantize it. And the good news is that we can quantize it correctly. We can quantize it completely. And this we have to do even at large n if we go to sufficiently long distances, long times. So for times of order n, we need to quantize it. And let me describe this boundary mode dynamics a little more. So it is important to describe it. It's important to understand the asymptotic symmetries of ADS2. So ADS2, as I said before, has some isometric group, which is SL2R. But if you only look at the reparametrizations or the coordinate transformations that preserve the metric near the boundary, but perhaps not the metric near the interior, then the group is bigger and it's the full time reparametrizations. So this is somewhat analogous to how in 1+1 dimensional conformal field theories, the symmetry group is enhanced to a Virasoro group. In this case, we have a similar phenomenon where the symmetries become these full-time reparametrizations. And we can think of these symmetries as being spontaneously broken by the ADS2 metric, because when we act with these symmetries, we change the metric. But we can also view them as, in addition, they're also explicitly broken by the boundary conditions, or the fact that we are not in exactly ADS2 space. And this leading breaking is just given by the Schwarzian action that we mentioned a few times. So this Schwarzian term is the leading operator that can break the symmetry and that can break the reparametrization while preserving the actual symmetry of the spacetime, which is SL2. And so this action then governs the dynamics of this. Now, if we have supersymmetry, we have a similar logic for finding the action. Again, we have some now supergroup of symmetries, which includes SL2 and then some other fermionic symmetries. And then we have a similar logic that gives us the supersymmetric version of the Schwarzian action, which contains these bosonic terms and then some terms involving fermions. I won't write down the actual action. Now, the extremely low energy theory has h equal to 0, and therefore it has no time dependence. So one interesting point that is in some sense at the very long times, the symmetries, this reparametrization symmetry is actually time reparametrization symmetry is actually restored. Okay. So that's just a comment. So now I'm going to review how these correlators were computed, first in the case without supersymmetry and then with supersymmetry. Now, these calculations, we did these calculations basically in the Euclidean case, where we start with a Euclidean black hole at low temperatures, low but finite temperatures. So the inverse temperature beta is then a circle of very long length beta. And so the idea is that we have the full Euclidean space, ADS2 is just hyperbolic space, which we can represent as a disk. And then there is some boundary at some finite location. And this boundary has a very long length, which is beta. We are at very low temperatures. And then when we consider this gravity theory, we can think of matter fields that move in a rigid ADS2 space. And this boundary becomes dynamical and fluctuates, as we had discussed before. So it's not just a rigid circle, but a circle that has fluctuations governed by the action we discussed a moment ago. And because of that, this boundary can be, it's one-dimensional and can be viewed as an additional particle that moves in ADS2. So, and the quantum mechanics of this boundary can be exactly solved, was solved in these papers. And it behaves essentially, the reason it can be solved is that it behaves essentially as a non-relativistic particle moving in ADS2 with an electric field, which is, you can view it as an analytic continuation of a problem of Landau levels, if you wish. So two-dimensional Landau levels, not on flat space, but on ADS2. And for the same reason that the Landau level problem is solvable in flat space, it's also solvable in a space with constant negative curvature. and for that reason, we can solve this problem. So this, I'm just giving you an intuition for why it is solvable. So in the end, so the final answer is that we can draw diagrams which are similar to the Witten diagrams we had before, except that now this boundary is dynamical. So there's an additional propagator that joins these 2 points. And these propagators have a given proper length, which is the proper time, which is the time according to the boundary observer between points 3 and 2. And they connect bulk points 3 and 2, for example, and we should integrate over all bulk points, all the bulk points, keeping this boundary distances fixed. Now in formulas, what this means is that the correlator from the full correlator, which depends on the boundary times, corresponds to a product of some correlator in a rigid ADS2 space without gravity, plus this additional boundary particle propagators. Or more precisely, we have some correlator in ADS2 that where the C dependence is relatively simple and the X dependence is a little more complicated. So C and X here are the Poincare coordinates of ADS2. And then we have the boundary propagators, which depend on these 2 bulk points and the proper time. And then we're supposed to integrate over all of this, and this gives the final answer. So I'm kind of sketching for you what the formula looks like. I'm not writing down the formulas explicitly, but this is a formula which we know explicitly and was computed in these 2 papers. Okay, so now we go to the supersymmetric case, and the good news is that the answer is very similar. And the new feature is that at long time, so times bigger than this beta naught. So beta naught is the time scale at which the Schwarzian dynamics become strongly coupled, or this is related to the coefficient appearing in front of the Schwarzian action. So this is this time scale, which is of order n. Then this propagator becomes completely independent of the boundary time. So, and then in this case, we interpret this as saying that only the zero energy states of the dual quantum mechanical theory actually contribute. And then in this case, the correlator becomes essentially, becomes topologically independent of time. So the formula is basically the same as the formula we had before. The only difference, the most important difference, is that this propagator is independent of the boundary time. So the correlators are independent of the points where you put the operator, as long as these points are separated in time by a very large amount. It can depend on the order of the operators, but is independent of the size of the time. And the final answer for the correlator is some number, and this number depends on the coupling constants you might have in the bulk theory and the dimensions of the operators or the masses of the fields that you have in the bulk theory. So we could wonder how we can have a theory with no Hamiltonian, how we can have a non-trivial theory with no Hamiltonian. Of course, the time evolution is trivial, but there is some information in the form of the observables. The idea is that the observables or the operators are chosen somehow a priori. So, I mean, if you were able to choose observables however you wanted, then we're just dealing with e to the s times e to the s matrices, so there is not much to say. But the idea is that the gravity theory or even macroscopic theory like SYK comes with a specific set of simple observables. In the case of gravity, correspond to observations of the fields of the gravity theory, local fields. And those then could have some interesting correlators. So when we project onto the ground states, this could become somewhat complicated matrices, which have interesting correlation functions. So far we've looked purely at Euclidean correlators, but in the bulk we can also continue them. We can imagine continuing this to a bulk Lorentzian continuation, and that so that we can continue. We continue to have a Lorentzian time in the bulk, even though we don't have a time in the boundary theory. So that's why I was saying this is a curious case. where it is clear that the bulk time is emerging not from the boundary time, but somehow from the structure of the algebra of these operators in a way that we don't completely understand. But we hope that to be able to elucidate by thinking about these correlators.
Can I ask a question?
Yes, please.
So if we have some conformal symmetry, usually 2-point function, it looks like 1 over, for example, u1 minus u2 to the conformal dimension.
Yes.
So, but so for supersymmetric case, you are saying that it is constant. That means some conformal dimension is actually 0, or
yes. So the idea. Let me. I'm going to go forwards a little bit. So here it is. So we computed this 2-point function that you are thinking about, right? And at short distances, it goes like relatively short distances. It goes like 1 over u. Okay, so that's this conformal invariant regime where the times are large, but not large compared to n, right? And then when we hit this beta 0, which is a time of order n, then the correlator becomes constant.
Let's see.
So the idea is that, so here is when the dynamics of the boundary mode starts being important. And this dynamics is not conformal invariant. It breaks the conformal symmetry. And so the answer that it gives is an answer which it's certainly different from this power law, which is what you would have expected on the basis of conformal symmetry. But it becomes constant. So in some sense, it would be consistent with a simpler version of the conformal symmetry where the anomalous dimensions all vanish.
Thank you very much.
It's a bit like a transition between two conformal fixed points. So there is some conformal theory here, and then here there is another one, but this one is kind of trivial, it's topological. No anomalous dimension.
This only happens for supersymmetric case.
Yes, so that's correct. Yeah, so if we were dealing with a non-supersymmetric case, this plot would have some power here, and then it would have a different power here at longer distances. That is again independent of the dimension, but it's some power like in this particular case is a power which is 3/2 in the case of the 2-point function.
Thank you.
That's right. Okay. Okay, let me go back here. So when we think about these infrared operators, what we have some simple operator in the theory, and then we evolve by a very long amount of Euclidean time. So here we say u equal to infinity, but as long as u is bigger, somewhat bigger than n, then we already are projecting onto some special operator, which will be more complicated. So this operator might be simple, but this operator will be a little more complicated. So for example, in SYK, O could be just a fermion or a product of fermions, let's say a qubit, and then when we do this, we get a more complicated spectrum, more complicated operator with a let's say almost continuous spectrum and so on. And in the bulk, the picture is that we insert some operator at some point, and the long Euclidean evolution attaches one of these boundary propagators, and then we get a state, let's say, of the two-sided system of a state in H left times in Hilbert space left times Hilbert space right, but consisting of zero energy states, and that this essentially corresponds to this operator O hat. Okay, so it has two indices, and so we can think of it as creating a state, an entangled state in two copies of the Hilbert space. Okay, so the 2-point function that I just mentioned is computed by a variety of methods, and we computed by some method. It was computed by other methods, or parts of the correlator were computed by other methods in these papers. And so we discuss now some these qualitative aspects. We already discussed that. Well, I already mentioned this. One point I didn't mention was that so this constant value is somewhat relatively small, because we have this 1 over u to delta, and we continue to have up to a time of order n, so we get something that goes like 1 over n to the 2 delta, and so this is something small, which for ordinary 4-dimensional black holes, this is n to the 2 delta, or the entropy to the 2 delta. well, 1 over the entropy, or 1 over n to the 2 delta. So it's somewhat a small, relatively small suppression. So how can we think about that? So the idea is the following. So we have some, I'm just restating what I just said. We could normalize the operator so that its 2-point function at relatively short time, so times of order the radius of the black hole, is of order 1. And then when we go to very long times, then this 2-point function will be very small, proportional to 1 over the entropy to the 2 delta. And we can, so this 2-point function gives us, we can view it as follows. So it gives us the, if we diagonalize the operators, then the 2-point function can be written this way, and so it can be viewed as giving us the typical eigenvalue of the operator. This typical eigenvalue is not the same as the typical matrix element of the operator in some random basis. So if you have, if you first diagonalize the operator, then we now have a single sum over alpha, and we have e to the s naught values for alpha. So this is just exactly the average value of the operators in this particular basis. And this is larger than the typical value of the 1-point function in a random quantum state. This is just the typical eigenvalue in a basis that diagonalizes the operator. Now, I think this gives an interesting implication for where geometry can start differing for various microstates, at least in this basis. So people have asked the question. So we know that the black hole has many different states. But when we look at the black hole, it looks like we have just a single black hole geometry. Now, when should the geometry start differing for the different microstates? Well, if we look at these correlators, we can interpret the suppression, which is universal for all these operators, as given by the propagation of a particle from the near horizon region to this point, by a distance which is proportional to the logarithm of the entropy. And so we would say that at least up to this distance, all the geometry should look, since we are reproducing this factor from this simple geometry, we expect that the geometry should be this ADS geometry. And then perhaps at this distance, it could start differing in some way for the different microstates. Now we'll discuss now a slightly different implication. Okay, how am I doing with time? Well, when we think about the quantum mechanics of the two-sided system, we have a basic observable, which is the distance between the two black holes, the distance between the two boundaries. So as time evolves, this distance starts growing and will become very long. And the dynamics is similar to the dynamics of an Einstein action. Oh, sorry, a Liouville action. This follows from the Schwarzian action we discussed before. It's just a restatement of the Schwarzian action in terms of the gauge invariant observable, which is the distance between the 2 points. Now, in a supersymmetric situation, we have a similar Lagrangian, but now we'll have some additional fermions. And we can find the eigenfunctions and so on. But the important point is that the answer is a bit long, and we can find the constant, etc. But the important point I want to draw your attention to now is that because of these extra fermionic terms, in particular these Yukawa coupling terms, when these fermion operators might have eigenvalues, let's say plus or minus 1 on various states, so effectively we have something that looks like the potential, repulsive potential we had before, but we might have some attractive term that is more important than long distances. And so we can have a potential that has a minimum like this, and so there might be normalizable states, and in particular, the coefficients here dictated by supersymmetry are such that there is precisely one normalizable zero energy state. And so that means that when you have the thermophile double, so these two entangled black holes at finite temperature, and you take the zero temperature limit, in that limit, all that will remain is this particular wave function for the ground state, So that, well, maybe I should have said, if you have the wormhole and you take this lower temperature limit, you will get this particular wave function. In particular, this is saying that the length of the throat does not become infinite, as you might naively think according to the classical theory, but the length of the throat of this wormhole becomes finite at low temperatures. In other words, we could wonder what happens with this ER equal to EPR relationship as we go down to the supersymmetric limit. So here we consider here a supersymmetric black hole, and very, very, very far away, a black hole with the opposite charge. So if they were very close, they would not preserve supersymmetry, but very far away, they approximately each preserve some supersymmetry. And then we can have a situation where we can have a supersymmetric wormhole, and it's given by essentially this quantum mechanical mode. So it's a wormhole of finite size, but where quantum corrections were important. Okay, so in the same way that we can talk about this length of the wormhole, we can think about the propagator. I won't discuss all the details. It's already somewhat late for you, but we can calculate the propagator at very long times, and it's somewhat simple. It's some specific function in ADS. And this propagator then can be used to do a variety of computations. So for example, we can insert a particle here, and we can insert another particle here to measure this length. And in this way, we can see that, for example, when we insert a particle, this length increases, the entropy decreases, the entropy becomes less than the extremal entropy. In fact, we can argue that we have the structure of the so-called type 2-1 algebra. Now, because we have h equal to 0, there is no chaos from energy levels. So it's been remarked in the last few years, particularly, and well, explored very beautifully in some papers of Saad, Schenker, and Stanford, that the distribution of energy spacings for black holes follows the distribution expected for a random matrix. That is what we expect for chaotic systems. Now, in this case, there is no such thing because all the levels are exactly degenerate. But the idea is that that the operators O hat, which are these projected operators to low energies, they behave a bit like random matrices, and with some evidence for eigenvalue repulsion. And we discussed a little bit what that evidence was in our paper. So in some sense, there is some chaos in operators, or perhaps their eigenvalues. Now, as a final point, let me just say that we can compute these 2-point functions numerically in the n equal to 2 version of SYK. I won't say what that exactly is. And we have a prediction from the quantization of the Schwarzian, n equal to 2 version, and then a numerical answer for some number of fermions, and it works pretty well. So the conclusions is that at these very low energies, we have some correspondence between ADS2 and something which can call the topological field theory 1. This is just a way to talk about the theory with no Hamiltonian. There is a sense in which we have a bulk time, but not boundary time, because we have h equal to 0. We haven't given a precise definition of this bulk time. We have only looked at some of its consequences indirectly by looking at the correlators. There are other interesting observables for supersymmetric ADS2, which are these correlators we computed. We computed the 2-point function, we computed the propagator, and that allows us to, in principle, compute any correlator. And this puts constraints on how different various microstates can be. Now, in the future, we'd like to have a better understanding of this bulk time, which is an important question. And we think this supersymmetric case, since it's more calculable, might give more insights. And finally, we would like to find eventually a gravity picture for the microstates, or understand whether it's possible or impossible, and so on, to get such a picture. Okay, thank you.
Okay, thank you very much. So everybody unmute and then just grab, please. So it's time for the question. If you have any question, please raise your hand, and then.
Sir, I have a question. May I ask?
Yes, please.
Yeah. Go ahead.
Yes, sir. So can the ADS to bulk geometry be also? Can it also be a representation of the Big Bang to inflation universe?
Yes, but that would be more like DS2. So you might imagine a two-dimensional model of a Big Bang where you have a two-dimensional expanding universe.
And does it have any kind of similarities with the algebra of this ADS2?
Maybe there was, yeah.
TFT1.
Yeah, so the algebra of the zeta space, it was pointed out that in the Larsen limit, it was again a type 2-1 algebra for somewhat similar reasons, in the sense that the total energy should be 0, right? And then and ADS space, this is not restricted to 2 dimensions, but in any dimension. So also the vacuum has the maximal entropy, and as you start putting in particles, you reduce the entropy. So it has those features in common with this model, but well, these are 2 models where the same algebra appears. I don't think they are related. I mean, the geometries are different. So one is somehow not expanding or collapsing like ADS, but the other one is expanding.
Okay, thank you, sir.
Sure.
Okay, so Yu Zhou Li, please.
Hi. I have one question for the coordinator. Very live question. So, is there a bulk point limit for the coordinator that may capture the flat space version of JT gravity?
That's a very good question. So the answer is I don't, well, no, well, at least I don't know of one. So this is something you can easily do, you can easily find in higher dimensions, so in ADS3 and so on. And there you can do it because you can rotate. So you have 2 points in the past and 2 points in the future, and you can rotate them in some angular direction. And then you can isolate the contribution that comes from the bulk point, right? But ADS2 has only 2 boundaries. We cannot really rotate it. And so at the same point that you would expect a contribution from a bulk point, you also have a contribution from just particles that propagate between the 2 boundaries, for example. So you cannot easily isolate the contribution from the bulk point.
Yeah.
Maybe there is some trick. We've tried thinking about this, but we didn't find a simple answer.
Okay. Thank you.
So Masaki, please.
Thank you very much for the nice talk. So I have a question about this thing on the slide. Can we get the gravity picture for the microstates?
Yes.
So using these topological correlators, these topological correlators are somehow giving some information about the structure of the microstates. But do you expect that? Do you expect how much can you expect to get from this? Are these correlators just giving us some averaged features of microstates?
Yes, I think they're giving us some average features. Yeah.
Yeah, so that sounds like you cannot really get.
No, you cannot get you cannot get the particular microstates or very fine details, because here we are getting average features where we sum over e to the s of the e to the s state. Probably to get to the microstates, one would need to understand also the higher genus corrections.
Okay. But if you consider higher genus corrections, do you get some more information about microstates, or do you get still some average?
I think in principle you might get more. We haven't done it. We haven't understood the higher genus corrections. So
but that sounds like, how much do you think you can get out of just gravity, classical gravity picture? Oh, this is classical gravity.
Yeah, so what we discussed goes beyond classical gravity, because it involves quantum gravity, but a very simple quantum gravity mode, which is this boundary gravity mode.
Right, but still the degrees of
So for example, in particular, the 2-point function that we discussed in answer to Tadashi's question.
Yes.
If you were to compute it just in classical gravity, you would get a 1 1 over u to the delta or 1 over time to the delta for all times, right? It will go to 0 at long times, but the quantum corrections implies it does not go to 0. So we've taken into account some perturbative quantum corrections within the class of the topology of the disk, but in principle, we could have some other topologies, and we haven't done the analysis of other topologies.
Right, but these are still gravity degrees of freedom. It's not stringy degrees of freedom. Do we not have to consider those stringy degrees of freedom to get farther?
Yes, probably. Yes, that sounds. Yeah, that's true. But well, in particular, for some of the discussion, even for the computation of the correlators we discussed here, you could consider operators which involve gravity fields and string modes or whatever. So those correlators will depend on the details of the geometry and the details of the string theory in principle.
Yes.
We only set the ground rules to compute the correlators, but not what they actually are in some specific case.
Okay. Thank you very much.
But I wouldn't expect those correlators to be able to be so fine as to distinguish between different microstates.
Right. These are only averaged correlators. Yes. Thank you very much.
But even though they are average, they just give a constraint for what. So if someone has, for example, in the context of fastballs, a proposal for the microstates, right? Then these correlators constrain the expectation value of the field. So if we have a microstate that has some various expectation values for fields far away, right? So these microstates break many symmetries and so on, and so they will lead to non-trivial expectation values far away.
Right.
So this cannot be too large somehow. Because we know the average value of the square, right? That's the given by 2-point function.
Right.
So it gives us a constraint, for example.
Constraint. Yes. Thank you very much.
Yeah.
Other question?
Sorry, can I ask a question?
Yeah, please.
So can we, you consider the n equal 2 case, can we consider less supersymmetric n equal 1 theory? Is it topological?
Good. Well, the n equal to, we didn't consider the n equal to 1 because in that case, we don't have this gap that we don't have exactly protected states at 0 energy. We also don't have this gap between those states and the rest. So in some sense, it's a bit more complicated. So the n equal to 1 is slightly more complicated than the n equal to 0, but the physics is somewhat similar. So for that reason, we were not so interested. So the n equal to 2 is a little more complicated than the n equal to 1 at the level of doing the gravity computations. It has a little more fermions, but we can cleanly separate the physics of the ground states from the rest. That was the advantage. We could consider also n equal to 4, which also supposed to have the same features. And people have considered some aspects of those theories, but yeah, there we expect a qualitatively similar answer, so we didn't do that.
I see. Thank you very much.
Can I also ask a question?
Yeah.
So you discuss in GN that the two boundary distance L is stabilized in finite distance. Naively, it's become ages to slot, so it's become infinity. But some n equal to case, some quantum effect make it. What do you have any intuitive understanding of why this such a stabilization occur and they make it finite distance?
Yeah. So it's related to this negative term that we discussed here. Let's see. So because we have these fermions, right? It leads to this attractive potential. And then it's kind of at finite distance. Now, there are other situations where you also have a negative term like this. For example, when you have if you had an interaction between the two systems, between the two boundaries, also you could give rise to terms like this. And in those cases, you can get a much deeper potential here with many bound states.
I see.
In this case, somehow it's perhaps somewhat similar that there is some correlation between the two sides, and if only the boundary fermions are correlated, it creates a tiny amount of negative energy, and this tiny amount is enough to produce just a single state.
I see.
Yeah, if we had many states, we might probably get in contradiction with causality, that you can send signals from one side to the other. But somehow when it's exactly at zero energy, and we have only one state, then we cannot use it to send the signal.
Okay. I also have another stupid question, if you don't mind. So when you mention the difference between SYK model and near extremal black hole, near ES2, the reparameterization model is matching by the Schwarzschild chain action. That's okay. But you say that the conformal invariant part for the SYK and then quantum field theory on the ADS2, even though the symmetry match, the physics doesn't match. You mentioned, is that right?
Yeah, that's right. So I mean, what I have in mind is that we don't know the exact dual of SYK, right? People sometimes think it's maybe n fermions in ADS2, maybe with some interactions. But we don't really know it, and we expect that if we knew it, it would be some model where probably somewhat similar to a string theory, where the string scale is comparable to the radius of ADS. So it's not in the Einstein gravity limit. Well, here on the right, I had in mind a black hole that is described by Einstein gravity.
Right.
So that's all that I meant to say with this.
I see. So it's like more like normal higher spin situation where the
yeah, it probably some kind of higher spin. It was not described in detail anywhere that I know.
I see. So the point is that even though the symmetry match, the spectrum, the gap doesn't match between.
Right. It's like the difference between, let's say, n equal to 4 super young mills at strong coupling versus weak coupling. Right?
I see.
So
this is more
coupling,
like
there is some Einstein gravity.
Version, right?
Yeah, that's right. Yeah, this is would be more similar, or maybe coupling of order 1, I guess.
So symmetry is not enough. You need the gap.
Yeah, and it is interesting that they have the same symmetries, so it's still they have the same conformal symmetry.
Right. Okay, that's. Oh, okay. So Tokyo, please.
Yeah, thank you for the very interesting talk. And so, actually, I also have a question on the Suji EPR part. And so I think so. If we put, if we try to make a wormhole, then so we should put charged black holes with opposite charge. So that will break the supersymmetry. So in that case, so doesn't it lift the potential so that we don't have any bound state? Or
Yes. So here I was having in mind these two black holes in two different universes, so that the supersymmetries are unrelated.
Exactly.
That would be like exactly the wormhole with no interaction whatsoever. So I mean, it's somewhat similar to saying that these two black holes are very, very far away, right? As you say, they don't preserve exactly the same supersymmetry, but they preserve different supersymmetries. If they are far away, you can think of these both supersymmetries acting independently on each one.
I see. So if we separate sufficiently two black holes.
Yeah, I think that's what I had in mind. But it's true that we could not do that by bringing them very close together. Now, there might be some circumstances where perhaps you could do that. So if you embed these black holes in some ADS space and so on, maybe in a curved space, it might be possible for there might be a global spinor that preserves the approximately Poincare symmetries of the two black holes. So for example, if you have ADS3 times S3 times T4 and so on. So I think in some of these cases, it's possible to have some charged particle at the north pole of the S3 and at the opposite charge at the south pole, right? Two opposite poles of the S3. And they preserve a supersymmetry. So those kinds of situations are possible. So yeah, that's an example where you have a curved space and the Killing spinor changes in such a way that preserve the.
So in that case, we can keep the supersymmetry exactly with distance between two black holes. I see.
You can make this more complicated construction perhaps, but it's somehow not too necessary, but because for making the basic point, you could just consider them in two separate universes.
I see. Okay. Thank you.
Sure.
Tadashi?
Yes, I have a question about this. So in the end, you mentioned that actually algebra looks like Dojita algebra, type 1, type 2, 1.
Yes, yes.
And in Dojita case, in my understanding, Dojita entropy gives kind of upper bound of the information we can accommodate in the Dojita universe.
Yes.
So is there something analogous statement for your case, ADS2?
Yes. So here it's important that we have the structure at low energy. So first we project onto low energies, right? And then in that situation we have a maximum entropy, which is when we have the sort of the standard, so the thermophile double state with no particles. And then any deformation we do, we expect that it would decrease the entropy.
Ah, I see. So
Yeah.
You have finite.
Yeah, so if you think in terms of this zero energy limit, this zero entropy state is just maximally entangled between all the ground states of the system. So those ground states are maximally entangled. You act with some operator, you change that.
Yes.
And the entanglement will not be as big. So for example, let me see, I think, we discussed before what happens when you act with some operator and you produce a new state. Sorry, I lost the transparency. Well, even in this case, so in this case, we acted with several operators. We won't have the maximally entangled state, so we'll have less entropy. We did compute in the paper the entropy for cases where you act with just with one. So we computed what this constant is. It's just some order one constant that depends on delta.
I see. Thank you very much. It's very clear.
Yeah, sure.
Chente, please.
Oh, thank you. I want to ask if we consider the micro-canonical ensemble, then what algebra should we get?
Yeah, well, this is the macrocanonical ensemble. So we also, I mean, in this case, the two ensembles coincide because the states are exactly degenerate. So if we go to very low temperatures, we focus on zero energy states, and we could also consider the ensemble of zero energy states. It's important that in these cases, we are considering this thermophile double where we entangled in two systems. That's what these gravity pictures are telling us.
Okay, so in this sense, okay, if we consider the different ensembles, the answer will be different or the same?
No, it's the same. It's the same. The two ensemble coincide because the Hamiltonian is zero. So
okay, so but what is the reason? Because I know that the Witten recent paper say that the algebra may be different if you consider different ensembles.
Well, that might be true in the for the case of non-zero temperature black holes, right?
Okay. Yeah, sure.
That's one of the cases they discussed. That's not what we are discussing. So
yeah, it's not different. Do you have an intuition to say when we can get the same algebra?
When we can get
the same algebra between the canonical and the micro-canonical ensembles?
Well, I think I would expect that normally when the energy fluctuations are very small, so when you consider very small band in energy.
Okay, so it means that if your temperature goes to a very small, then you can expect to get the same algebra.
Yeah, that's what I would expect in this case.
Yeah, thank you. Yeah, thank you.
Sure.
Masaki, you have a second question? Or?
Yes, may I ask a second question? So you got this decaying correlation function by looking at this one loop correction by this Schwarzian theory. Yes. But on the other hand, in JT gravity, I think SAD computed also a correlation function using higher genus JT gravity and got this non-decaying correlation function.
Yes.
What's the relation?
Yes, very good. Yes. So yeah, we discussed this, right? Yes. Now, this calculation was at the level of the disk, so it does not include exponentially small corrections.
Indeed.
Right. And so SAD's discussion was about the exponentially small corrections.
Mm-hmm.
Now, here we got a relatively large answer. So it's only not exponentially small, So in his case, he would first consider the non-supersymmetric case where the tree level, sort of this answer would decay to 0, right? And he will look at times which are long enough so that this leading order answer decays to something very tiny, and then the exponential correction becomes important.
Right.
Now, in principle, there could also be exponentially small corrections to this formula.
But this one is power. I see.
Yeah, this one is just the power, and will be bigger. So the exponentially small corrections, at least to the actual value, will be small. So we could ask other questions about exponentially small corrections, but they will not be the dominant contribution to.
I see. So it's a different problem.
Yeah, it's a slightly different problem.
Okay, thank you very much. Thank you.
Tomonori?
Yeah, so I have a very naive question. So suppose that, okay, we generalize this 2-point calculation of a 2-point function to any point function. Does it have to do with multi-center black holes?
No, it's just a single black hole. So we're computing the 2-point functions in a single black hole. So let me. So those were the diagrams I was trying to draw here, for example, right? So this is a Euclidean black hole. So it has the topology of a disk, right? And then we consider the many operators. So it's just some some calculation we do on the original black hole geometry.
I see. Yeah, thanks.
Multi-center black holes might be additional corrections with different topologies and so on, which were not included here.
All right. So no more question. So okay. So thank you very much for Professor Maldacena for wonderful.
Thank you very much for the invitation.
Answering many questions. So thank you very much. So it's great. Thank you very much.
Thank you. Bye bye. Have a great night.